The equation we were finding, that polynomial that we used to find all the eigenvalues, that's called the characteristic equation. So this is our function regardless of which way we do the subtraction. The problem is that even in small matrices, I have a lot of different options when I go to find characteristic equation. All of the problems we did were rigged. And trust me, you will be very happy that I'm rigging these problems. This is a good thing. But let's look at some characteristic equations and what comes out algebraically as a result of our characteristic polynomial. Find me the determinant, find me the polynomial. You don't even have to solve it, write out the polynomial. Let's find the eigenvalues. We'll do that afterwards. Notice I did it the other way around than I did it last time. Ooh, the horror. So the determinant of A minus lambda I in this case is 2 minus lambda quantity squared minus 7 squared. Which gives me a quadratic equation. Which happens to factor nicely. So the eigenvalues are pretty nice. 9 and negative 5. Once again, not particularly ugly, a nice quadratic equation. Which factors? But this is a perfect square, which means I only have one eigenvalue. And as we saw, if I have fewer eigenvalues, I may get more than one vector for the same eigenvalue, right? So I could have one eigenvector, or I could have two here. I don't know. I know I only have one value. I don't know what the matrix is going to reduce to when I'm done. There's no tape. As long as I'm writing a 2 by 2 matrix, I'm going to end up with a quadratic equation. What are the roots of this one? It has no roots. Every quadratic equation has roots. He's shaking your head at it. I can't factor it. It doesn't mean I can't find the roots. It means I need to use the quadratic formula to do it. I can't say the quadratic formula anymore. I'm required to sing it. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Stupid thing is stuck in my head with a tune now. One of the students taught me that about 5 years ago. I haven't gotten it out of my head since. Two plus or minus the square root of negative 2 squared is 4. 4 times 1 times 1 is 4, but it's negative and negative. That makes it a plus 4. So I have 2 plus or minus root 8 over 2. Root 8 is 2 square root 2, which means everything is divisible by 2. And I get 1 plus or minus root 2. I'm already unhappy because if I need to go do reduced row echelon form of things with square roots in it, my calculator is going to barf on me and give me ugly ass decimals all over the place. Nothing here is wrong. Those are the correct eigenvalues. But working with that is just nightmarish, right? Try this one. Wow. There you go. Doesn't factor. If you're looking at this and you're going, I don't know, then don't try. Rip out the quadratic formula. Tell me what you get. I'm sorry? It's worse than that. The previous one was irrational. 9 squared is 81. 4 times 32 is 128. 9 plus or minus the square root of negative 47 over 2. My roots are complex numbers. I don't quite have the comedic effect emoji from The Mask with the eyes bulging out. Oh! Those are right. And here's the problem. All of these are meaningful. They all have valid interpretations, like what we were talking about on Wednesday. There's some sort of line or some sort of behavior as a transformation from R2 to R2. Remember, we're flipping them, keeping the line the same. This has to do something on the plane. My problems are not algebraic, although the algebra is complicated. My problem is that what was, take a determinant, which is a straightforward calculation, became solve a quadratic equation, which gives me all these different options that I now have to figure out what the hell they mean. It is, unfortunately, not trivial to work my way through all the different interpretations of all the different things. I'm going to put that on pause for a moment and deal more with just some of the algebraic issues I have. Because I'm taking a determinant. We had lots of different things to do with determinants, right? We had row operations. We had all sorts of properties about determinants and the things we knew. Let me back up and talk about determinants again and remember some things. Okay. We have had before a singular matrix has a determinant of 0, an invertible matrix has a determinant that's not 0. We know that the product of two matrices, when you take the determinant, you get the product of the determinants. That we have the same determinant if we switch rows with columns. So the transpose and the original equation, the original matrix, have the same determinant. We know that if we are looking at a triangular matrix, then all we have to do is multiply the diagonal entries. Capital P, capital Pi, product, like capital sigma, sum. Swapping rows multiplies the determinant by -1. Multiply row by some constant, multiply the determinant by that constant. Elimination operations don't change determinants. So if I want to find a determinant, which is really what this characteristic polynomial thing is, I can use all of these tricks. Problem is there are still lambdas floating around in my problem, yes? So when I do some of these row operations, the algebra may get trickier. But if I have a particularly large matrix, a 4 by 4 or 5 by 5, taking the determinant using cofactor expansion, that's a tedious recursive process. I go from 5 by 5 to 4 by 4 to 3 by 3, and it would be easier if I could just do some row operations and get rid of some numbers. And maybe pick rows particularly well or columns particularly well if I got lucky. But let me put all of this together. Let's take any matrix that I want to find the eigenvalues for. I could do some row operations to make it triangular, right? Once I've kept track of that, I just have to look at what's on the diagonal. And then I know what the eigenvalues are. Then, if the numbers are on, if there's a 0 on the diagonal, it must not be invertible. Which means, since the eigenvalues come from the diagonal, A is invertible if and only if 0 is not an eigenvalue for A. Huh. Our characteristic equation, our characteristic polynomial, is the determinant that we find in doing the eigenvalues. So the roots of that polynomial are my eigenvalues, and that means finding eigenvalues is finding roots, and that means I may need to do some weird. Let's find the polynomial for this one. We don't have to find the roots yet. Let's just find the polynomial to start with. My first reaction was I was thinking, hey, the bottom row is going to be really nice, except then I end up putting a lambda in it. Phooey. If I wanted to start doing some row operations here, I'd need to make a 1, right? Where would the 1 go? Normally go in that upper left corner, yes? Where there's a lambda. I would need to divide by the number that's there, and that would give me 1 over lambda minus 1 floating around. I think I'd rather hit myself over the head with a textbook. I don't want to do that. Which means I'm probably better off just going ahead and doing the regular cofactor expansion. Either across the top row, bottom one, because there I have zeros. That'll give me 1 fewer term to deal with. Go across the top row. Like I said, here's where it gets kind of ugly. I'm going to stop right there. And I'm going to say that I'm not at all thrilled about this, because that's a cubic equation. If I finish multiplying this out, I'm going to get a lambda cubed. And there is a formula for factoring cubic equations that I don't know and don't want to know. It's this big and it's atrocious. It's called Cardano's formula, and it's not worth it. How do I figure out where that's equal to 0? If I'm not going to try and factor it. That'll just give me -6 plus 12. That's the y-intercept of this graph, not an x-intercept. If I plug in 0, that gives me a spot on the y-axis. I want to know where we cross the x-axis, or the lambda axis in this case. Not a bad idea, but wrong way around.
What if we make this whole part of the equation equal to 0?
Well, but how would I do that? If I set that equal to 0, what do I do next? I mean, I could do all the algebra on the left-hand side. I could multiply all that out and gather all my like terms and get, let me see, lambda cubed minus 4 lambda squared. Then I get 3 lambda minus 3 plus 6 is plus, no wait, that's plus 3 plus 6. That's plus 9 lambda minus 6 plus 12 is plus 6. No, I'm not sure this is any nicer this way. So that to me, that was, you know, for lack of a bad pun, that was mental arithmetic that I shouldn't have even bothered with. So if I'm here, how can I figure out where that is 0?
If this is what you're thinking, but if you subtract 12 from both sides and you find out the left half is equal to -12.
But there are infinitely many ways to multiply two real numbers together and get 12. I could do a half and 24. I could do 1 and 12. I could do, okay, no, that's gonna really take a long time. It's actually much harder to solve things that aren't equal to 0. So leaving it equal to 0 is actually the best idea. But I still don't know what I'm supposed to do. In this room right now, somewhere on the order of $40,000 worth of technology that not one of you has suggested we use. I've got computers and phones and iPads and calculators. Let's graph this thing and see where it crosses the x-axis. Let's throw it into Wolfram Alpha and say, hey, where's this equal to 0? I mean, I have this during the exam. I should probably learn to use it. Let's graph this up. And I don't even need to multiply it out. I can graph it just by typing in that equation. So it'll be parentheses x minus 1, parentheses x squared minus 3x plus 6, close the parentheses, plus 12. And I take a look at that graph. Well, crap. This crosses the x-axis once. I have one real root. This is a polynomial of degree 3. Where are the other 2? They're imaginary. They're complex numbers. If I only have one place where I cross the x-axis, the other 2 need to be complex numbers. So here's another problem. Even if I do all the algebra right, I could be looking at this going, now what do I do with this? Because having this irrational root somewhere between -1 and 0, and two complex roots means I haven't the foggiest clue what's really going on here. That's probably the politest way I can say it. Even if I work out the polynomial and it factors and I get nice roots, I'm really, really happy to see this one. What are the eigenvalues here? Ta-da! It's triangular. I don't have to do shit. But what that means is that one of those is a repeated root, which means my characteristic polynomial would factor if I were to do all the work, which I'm not going to. I would end up with this. And that repeated eigenvalue, wait a minute, I got to go all the way back to regular algebra class, before Calc 1, before pre-calc. When the power up there on the factored bit is even, we touch the x-axis without crossing it. The power's odd, we cross. So this has 3 roots, and I could graph it. Over here. Parentheses, x minus 5 squared, parentheses, x minus 3, parentheses, x minus 1, not 3 again, 1. We cross the x-axis at 1 and 3, and we just touch it at 5. Those are roots with higher, there was a term for this. Had a higher power than just 1. Had a name for what that was. So there were repeated roots, right? Happened multiple times. Called it multiplicity. Now, I want to be a little more pedantic here because I got this from the equation. I'm going to say this is the algebraic multiplicity. This, by the way, in the section is example 3. I stole this right out of the textbook. Example 4 does something similar. But if there's an algebraic multiplicity, then there must be some other adjective multiplicity. I wouldn't specify it if I didn't have a reason to. So in addition to an algebraic multiplicity, we also have a geometric multiplicity. And this has to do with the size of the eigenspace. How many dimensions is it? Is it a line? Is it a plane with 2 dimensions? Is it a space with 3 dimensions or more? This is the dimension of the eigenspace associated to that value. It turns out the algebraic number is the bigger of the 2. Your geometric is never bigger than your algebraic, which means for 3 and 1, the geometric multiplicity is 1. For 5, it might be 1, it might be 2. I don't know until I work out the eigenvectors and get a basis. The algebraic multiplicity is bigger than or equal to geometric multiplicity. What are the eigenvalues of A? What are the eigenvalues of B? Both times, each twice, right? A lot of 2's in this answer. Huh. But that means that the polynomial for A and the polynomial for B are the same. One of the things common in mathematics is to try and figure out what changes, what doesn't, when I do stuff to a matrix, right? And we're doing that with the determinant the whole time. The determinant of both of these matrices is 4. If A and B are both square matrices, I say that A is similar to B. If there's some other invertible matrix, when I multiply by that matrix on one side and its inverse on the other, I can turn one matrix into the other. This is a way of connecting different matrices with each other. This is different than row equivalence. Matrices may be similar without being row equivalent. Matrices may be row equivalent without being similar. For example, these two up here are row equivalent. The reduced echelon form of both of them is the identity, which means I could write a bunch of row operations to get from one to the other, but they're not similar. Now, similar here means this particular definition of similar. They kind of look alike isn't similar in this case. We use this so often, we think of this as a transformation on the set of matrices. Taking the matrix A and mapping it to P inverse AP is a similarity transformation. It turns out we will use this similarity transformation later. There's a similar idea in group theory. There's a similar idea in graph theory. There's a similar idea in lots of fields of mathematics where we talk about how we look at connected collections of objects. And in this case, I'm thinking of the vector space whose elements are matrices. Similar matrices share the same characteristic polynomial. They share the same eigenvalues. They share a whole hell of a lot. I need you to go back to discrete. The very last topic we covered in discrete, equivalence relations. We took a giant set of things and defined a relationship between them. In this case, that relationship is similarity. Then I said, hey, these break up the entire space into classes. Similarity is an equivalence relation. Not only do similar matrices share the same eigenvalues and the same polynomial, they share the same rank, the same trace, the same determinant, the same nilpotent index, a whole bunch of other crap. The same Jordan normal canonical form. I don't even know what the hell that is. There's so much that connects similar matrices. Looking at this idea turns out to be a lot of value to us. And it boils down to the way in which we look at the eigenvalues and eigenvectors. So I want to look at some of the ways similarity helps us and what information I can get about classes of similar matrices. That is Wednesday. On Monday, if you have questions, feel free to email me. I will be glad to answer them. The keys will be posted in about another 2.5 minutes, and we'll be good to go. I need to look at the first exam before you all run off for a second so I can remember something. I don't have the original copy of the first exam. Hang on.